Hello everyone, this is Mustafa here, solving soil mechanics problems for civil engineering students. In this video, I'm talking consolidation, and this is question number 2. Let us see what we've got here. We are given a soil profile, and we are being advised that this is a proposed fill. We are interested at this stage at point B, given that a test done at point B showed that the pre-consolidation stress was 88 kPa. So given soil profile, pre-consolidation pressure sigma dash C, and required first to determine the soil history, whether the soil is normally consolidated or over consolidated, and then we determine the pre-consolidation margin over the in situ stress, and then we determine the over consolidation ratio, that's called OCR. Solution strategy for problems of that nature. First, we determine the in situ stress, that's sigma dash V naught. When we talk consolidation, we are talking effective. And then we compare the in situ stress sigma dash V naught with the pre-consolidation pressure given as 88 kPa in this case. Now, there is essential knowledge that we need to have to be able to solve a problem of that nature. First, we need to be able to define what a normally consolidated soil is versus over-consolidated soil, and also the OCR. The OCR is a simple definition. It is basically the ratio between the pre-consolidation pressure, sigma dash C, and the in situ stress, sigma dash V naught. Essential knowledge also is to know how to determine the in situ stress within any point in this profile here. Now, before we move to the next slide, there is another request here, that is at this point A, it says if the fill is applied, what will be the state of consolidation at point A? So what will be the consolidation state at point A after the fill is applied? Assume sigma dash C to be exactly the same. Now, before I move next, let me define the normally consolidated and over consolidated soil for you here. You need to understand the physical meaning of it, and then you can express it using your own words. A normally consolidated soil is that soil that has never seen in its history any stress greater than what it currently has. So this is a normally consolidated soil. This soil, we call it a virgin soil. Again, it is the soil that never saw stress greater than the in situ stress it is currently carrying. And over consolidation soil is basically the opposite. It is the soil that has seen in its history stress greater than the in situ stress it is currently carrying. So this is the meaning of over consolidated soil. Let us see how we can solve this problem. So at point B, based on our solution strategy, you are required to calculate the effective overburden pressure. We ignore the fill because this is the instruction here. On that page, it says these computations are based on the initial conditions and thus shouldn't include the weight of the proposed fill here. Okay, now let us calculate the in situ stress at point B. Now, there are two methods. I will try both, although I prefer this first method. Method 1 is to directly calculate the in situ stress effective at this point. Basically, you add all the submerged weight above the point of concern. So this is the ground surface here, given we are ignoring the fill. So I have to take note of the position and the presence of the water table or groundwater table. I have the groundwater table here at 1.5 meter. So for the effective stress to be calculated, we add everything submerged above point B. So I have 1.5 meter, that's times 18.5 bulk. And then I have 2 meter submerged because this 2 meter, actually they are below the groundwater table. So 2 times 19.5, take away the unit weight of the water 10 because this layer is submerged. Plus, I have 3 meters of clay. I multiplied also by the submerged unit weight, that's 16 below the groundwater table. So I take away 10, and this has given me 64.75 kPa, and this is method 1. Now for method 2, we make use of the correlation between the effective stress and the total stress. This means that we first calculate the total stress at point B, and then we take away the hydrostatic pressure. At point B, the total stress is summation of all the weight above me. So I have 1.5 meter times 18.5, and I have 2 meters times 19.5. That's saturated unit weight. That's inclusive of the water within the soil itself, plus 3 meter times 16, and this has given me 114.75. So the next step is basically to determine the hydrostatic pressure. I have here a triangle hydrostatic pressure, 2 meter plus 3 meter, that's 5 meter, multiplied by 10 for the unit weight of the water, that's 50 kPa. All I need to do now is to subtract the pore pressure, hydrostatic, from the total stress 114.75, take away 50, that's 64.75, exactly the same value I calculated. Obviously, this method is faster. Now, let us compare the pre-consolidation pressure 88 kPa versus the in-situ stress 64.75. So based on our definition, it means that the soil saw in its history a value of 88 kPa that is greater than what it is seeing at the moment, being 64.75. So based on the definition, the soil is over-consolidated at this particular point, point B. And the over-consolidation margin is basically simply the difference between 88 kPa and the 64.75 kPa. So I have here 23.25 kPa as over-consolidation margin. What remains is the over-consolidation ratio. Simply, it is the ratio between the 88 and 64.75 by definition. And this gives me 1.36. So the story here is that the clay at point B is over-consolidated because it saw in the past stress value of 88 kPa greater than what it is currently seeing from this profile of 64.75, giving me the over-consolidation ratio of 1.36. Now, what's next? It says, after you apply the fill, what will be the condition at point A? Let us see how we can address this. Basically, at point A, we need to calculate the in-situ stress before applying the fill and after applying the fill. And then we compare it with the pre-consolidation pressure that the clay saw in its past, given 88 kPa. So let us now calculate the in-situ stress at point A before the fill, exactly like we did at point B. So I have 1.5 meters times 18.5, plus I have 2 meters times 19.5 underwater, so take away 10, plus 4 meter here of soft clay underwater, so take away 10, and it's 16. This is the unit weight, saturated unit weight of the clay, so I have 70.75 kPa. The clay at point A is seeing or feeling 70.75 kPa compared with point B, which is feeling only 64.75. So we have to interrogate the results. Point A being deeper than point B has more pressure. Yes, 70.75 compared with 64.75. The difference is 6 kPa, yes, because this is 4 meter, 3 meter, so 1 meter deeper, times 6, which is the submerged unit weight here when we take out the water, the unit weight of the water, 16 minus 10 is 6 kPa, so this value makes sense to me. So now we just simply compare 88 kPa in the past compared with 70.75 present, so the clay is over consolidated at point A before the fill is applied. We repeat the same story again after the fill is applied. So the clay is filling 70.75. Now you are coming to add 3-meter fill over a wide area. Means that every single point laterally and also with depth would feel the brunt of the 3 kPa in full. So this is why at point A plus what it was experiencing before the fill, that's 70.75, it is now feeling additional 3 meter of fill multiplied by 19.2, that's 128.35 kPa. So what I am now facing is a situation that clay at point A saw in the past 88. Now after the fill it is seeing 128. So by definition it is currently seeing greater than everything else it saw in the past. So the clay is now normally consolidated at point A. Before you apply the fill, it was over consolidated. After applying the fill, it is now normally consolidated. It all depends on what is the soil feeling at the moment compared with what it felt in the past. So one important thing to note, which I already explained, is when you apply a load or a surcharge over a large area, it is being felt equally everywhere within the soil medium below it. So this is what this observation is basically saying here, and we applied this already to point A, feeling the brunt of the weight of this fill. Now I will ask you another question just to consolidate another piece of knowledge. How does the over-consolidation ratio profile normally look like within a soil? Not necessarily related to this, but this graph, you need to see it and you need to feel it and understand it. And this is the depth and this is the over-consolidation ratio. So normally for a profile, a uniform profile here, you see the over-consolidation ratio. Basically, it tapers or reduces as you go deeper, because if you have here a weight, it means that basically when you divide the pre-consolidation pressure by the in-situ stress, if the pre-consolidation pressure is the same and the in-situ stress increases, it means that the over-consolidation ratio will always decreases, and the minimum value you can ever have is 1, because at this moment you would be dividing the in-situ stress by itself, and this gives you 1. I hope you benefited from this problem, and I will see you guys in a next video, hopefully soon.